All right, we are now recording. Let me even turn on the projector. And the only announcement we had left was the one about the biopharma manufacturing 1 week summer thing. They paid $1,000 and travel. Well, someone got that off the desk and took it home. So I don't have that website anymore. I can probably go find it again if anyone needs it, but I'm probably going to quit announcing that one. The deadline's sometime in January. I don't know when. You'd have to go to the website to find out. Oh, and let me give you these other little tidbits. Seemed like there was something else happening. Well, oh yeah. Is this the only class you're taking here? Okay, well then it probably won't bother you, but on Thursday, I think we're supposed to have a faculty staff meeting, usually mid-afternoon, 2:30, something like that. I hope I won't have to go because I've got a class then, but if I do, then I'll hope to leave in time to get back for the class. But anyway, I was going to say if you had other classes on Thursday afternoon, you might want to check with your instructor today to see if he's going to that meeting or not, he or she. If they're an adjunct instructor, they're not required to go, so the class would probably still meet. If it's full-time instructor, that's 50-50 whether they go or not. So anyway, just let you know that. Friday, I will not be on Birmingham campus. We've got to go out of town this weekend, so we'll be leaving Friday morning. So I'm taking 4 hours personal leave on Friday. So I won't be on Birmingham campus Friday at all, or this campus either, okay? Now, sort of a good news, bad news situation here. The bad news is next Monday is a holiday, Veterans Day. The two-year system closes that day. Not many other states do this, but Alabama tends to do it. I guess we have a lot of veterans. I don't know. But anyway, there will be, this college will be closed on Monday. But the good news is it won't affect us any because we meet on Tuesday and Thursday. So that won't cost us anything. All right, so that's that. Now, next Tuesday and perhaps Thursday too, if these are the only 2 days you're on campus, you may see some people you don't recognize walking around campus. I tend to say suits, but they won't necessarily be in suits, but they'll be pretty official looking, I think. What we're having happening next week, Tuesday, Wednesday, and Thursday, I believe, is our once a decade, hopefully, no more often than that, SACS accreditation visit. Now, we've been getting ready for this for years now. We've been doing all the paperwork, all that's done. They come for the on-site visit next week. I think Tuesday, Wednesday, and Thursday. If they finish early, that's good news for us, and maybe they won't stay so long. But where we're getting with that is if you do see them, be kind to them, okay? Don't say, who are you, stranger, because they may be our accrediting agency. So hopefully that will go pretty smoothly. All right, that's, I think, all I can think of now anyway. All right, I believe we had started in 3.4 last time, right? We had talked about the adjoint of a matrix, and we did that in example 1. But we didn't get far enough along to say, why in the world do you even need an adjoint of a matrix? Well, here's where it's getting to. Top of page, okay, chapter 3, determinants, 3.4, applications of determinants, and page 129. The inverse of a matrix can be acquired through its adjoint. So what we have here, okay, if A is an n by m matrix, okay, in other words, square matrix, got to be, and it's also invertible. For what follows, it also has to be invertible. Then the inverse of A is equal to 1 over the determinant of A times the adjoint of A. And this was the symbol we used last time. It doesn't have a handy-dandy thing like determinant does, 2 straight bars. Now, if you recall, we did a shortcut on the 2 by 2 matrix when we're doing its determinant. Inverse, okay? Remember, we did 1 over the determinant, just like this, and then we did the adjoint. Well, the adjoint of a 2 by 2 is just what we did, you know. So that's why it worked before, because of this theorem here. But this will work for any square matrix, okay? And they do take you through a proof there. If you, I would say, knock yourself out on the proof, okay? If you want to see me do, if there's some steps you don't see how they get, I'll be glad to try to do it, but we'll do it. And that little remark on the inside margin there is about the 2 by 2 matrix. What we did was exactly taking the adjoint, though with a 2 by 2 that was so simple. All right, so let's do example 2. I think I'll clear the screen just because I might need all the space we can get. Use the adjoint of A to find A inverse, where A is -1, 3, 2, 0, -2, 1, 1, 0, -2. Now, I don't know how long your memory is, but if you recall, this was example 1. That was matrix A for example 1. Exactly. And example 1 was finding the adjoint of it. Well, we did that last time, so I don't want to redo it. So let's just write down the, sorry, I get this drainage and it just almost chokes me. Okay, the adjoint that we found last time of A, we found to be 4, 6, 7, 1, 0, 1, and 2, 3, 2. All right. So, how do we find the inverse of A, given that we already found the adjoint of A? What one other piece do we need? The determinant of A. So let's do the determinant of A. And since it's a 3 by 3, to me the easy way to do that is -1, 3, 2, -1, 3. 0, -2, 1, 0, -2. And 1, 0, -2, 1, 0. Okay? This is going to find, now that's not correct to put vertical bars because that's not a square matrix, but you know what I mean. Okay? So what you get here, determinant of A is equal to, that gives you a -4. This gives you +3, and that gives you nothing. Okay? So let's get those out of the way. And do our up diagonals. That gives you, okay, but it's negative because it's going up, so that gives you a +4. So that's going to wipe out that one. Okay, fine. That gives you nothing, and that gives you nothing. So your determinant is 3. Okay, what do you do with the determinant? You got it. And what is that? A inverse is equal to 1 over 3, 1 over the determinant, times the adjoint, which will be 4, 6, 7, 1, 0, 1, 2, 3, 2. Now, frankly, I would be perfectly happy leaving it like that. I have a feeling the book is going to actually multiply that through, so I will. That would be 4/3, 2 7/3, 1/3, 0, 1/3, 2/3, 1, 2/3. Okay. I don't know if they, yeah, they did. I thought they would. 4/3, 2 7/3, 1/3, 0, 1/3, 2/3, 1, 2/3. And they say check that this matrix is the inverse of A by showing that A times A inverse is equal to I. And then they said also do A inverse times A. I'm not even going to do one of them, okay? So let's do it real quickly. Let's do A times that. So that's our answer, but what I'm going to do is multiply A times that and see what we get. This is -1, 3, 2, 0, -2, 1, and 1, 0, -2. So, is that doable? Yep. 3 by 3 by 3 by 3 is going to be a 3 by 3. Okay? First entry, 1, 1 entry. Would be a first row times first column. -4/3 plus 3/3 is going to be -1/3 plus 4/3 I get it as 1. Yeah, okay. Okay. I hope so. That's what we want it to be. Okay, let's do 1, 2 entry. First row by second column. -2 plus 0 plus 2, 0. Good. First row by third column. -7/3 plus 3/3 would be -4/3 plus 4/3 is 0. You see it? Okay. 2, 1 entry. Second row, first column, 0, -2/3, +2/3. That's a 0. Oh my goodness. My throat hurts. 2, 2 entry, second row, second column, 0, 0, 1. Good. Second row, third column, 0, -2/3, +2/3, that's a 0. Sorry. I'm having an awful lot of drainage and it's hard to talk. All right. Third row, second column. Oh, we're going to double the class size. All right. No problem. Good to have you here.
Don't be alarmed. That's question 2 right there.
Okay.
It took me more time on that one, and I just had to start over again and try
Right.
to figure it out. But you'll find 1, the rest of 1 through.
Right.
And just 2 is right here.
2 is okay. All right. Good deal.
Sorry about
Thanks.
that.
So it's a, what do you call that? Scavenger hunt to find your answers. Okay. Got it. No, I'm just kidding.
It took me, I was up all night.
Oh.
And I gave up, and I started over again. Did nothing. I was talking with my wife, and it came to me
Right.
how to go about it. I hope it, I'm not sure if it's right, but
Okay.
I had a couple of different answers.
Right.
Went about it a couple of ways.
Yeah.
I couldn't figure out. I think it was number 9.
Right.
I taught you my hands up without.
Oh, okay.
You won't see that.
Yeah, if I remember right, yeah. Okay. Now that was test 2 or 3. That's the one that we're just finishing today.
Yes, sir.
Oh, okay. Now wait a minute on this. That's what I gave it to you. Yeah, we haven't even. Oh wait. Oh, you did Kramer's rule. You did 10 already.
Yeah, I kind of figured that one out because I went through the book.
Right.
Or the notes that I had.
Yeah, because these weren't due until we finished this section.
Oh. Well, I used the chapter and then went back over the videos.
Right.
And comparing.
Yeah, but we haven't finished 3.4, so we haven't even done Kramer's rule yet. Do you want to hang on to it a little bit longer in case we do something? I think we already passed 9, but if
we did cover. Anyway, I was able to kind of figure it out.
Oh yeah, okay. Well,
I think
yeah, that's why I gave it to you last time, just so you'd have the weekend to work on it, but not. Well, so you had to finish it the weekend.
Yeah, I'm tired of work. I'll probably be in Thursday.
Okay.
I'll have to go out of town again.
Okay.
So I better try to do as much as I could.
Okay.
Be late getting in.
Right. Okay. What we're doing now in 3.4 is finding the inverse of a matrix by its adjoint. There was the matrix, and the adjoint we had found last time, because that was example 1. We're doing example 2 now. Example 1 was find the adjoint of it. We did. So rather than redo that, I just wrote it down. And then we did the determinant of A. Because it was 3 by 3, we used our expanded 3 by 3 matrix. Down diagonals, up diagonals, that kind of stuff. Excuse me. Found out the determinant was 3. And then the theory here says what you do is the inverse of the matrix would be 1 over the determinant, so that would be 1/3 times the adjoint. And so we did that and got this out. Now we're checking it by multiplying A by the inverse, supposed inverse, to see if we get the identity matrix, and we are well on the way to getting there. We got one more row to go, so let's do row 3. And I've got a sore throat coming on, so my voice is messy and hurts. So I may have to stop and choke a little or something. So let's do the 3-1 entry, 3rd row, 1st column. Okay, that would be 4/3, 0, minus 4/3. Sure enough, that's a 0. The 3-2 entry, 3rd row, 2nd column, 2, 0, minus 2, that's a 0. Oh, if we can just get this last one. The 3-3 entry, 3rd row, 3rd column, 7/3, 0, minus 4/3. 7 minus 4 is 3/3, which is 1. Yes, yes, yes. All right, so I did the A times what we thought was A inverse, so you can do A inverse times A. It's going to give you the same thing, but if you just want the practice of doing it, do it. Now we turn the page to page 130, and this is where we do Kramer's rule. Now, we haven't done that already, have we?
I thought we touched bases on Kramer's rule in chapter 2, or
we touched base on determinants in chapter 2, but did we do Kramer's rule?
We did. Yeah.
Oh, well, maybe so.
Chapter 1 or?
Okay, let me just see. Oh, it doesn't list here. That's not this. Let's see. Kramer's rule. Kramer's rule. 124 is the first place. Oh, I guess we did it. Oh, it's just mentioned at the bottom of page 124. But we really talk about it in 130 and 131. And they talked about Gabriel Kramer there too, who, by the way, is another potential paper topic if you wanted to do that. All right, so let's do Kramer's rule, named after Gabriel Kramer, 1704 to 1752. Just to get an idea, Alabama wasn't even thought of at that point, okay? The U.S. was not even in existence at that point. This was Georgia wasn't even a colony at 1704. It had become a colony by 1752, if not for very long, okay? So he was way before us. Now, Gabriel Kramer, I don't know. The name also almost sounds a little German, but it could be British, it could be anything. Don't know. They don't give enough here to let you know. But Kramer's rule, named after him, uses determinants to solve a system of n linear equations in n variables. Okay, so it has to be square, in other words, n equations, n variables. The rule applies only to systems with unique solutions. It will not work if you have multiple solutions or no solutions. Okay? So to see how Kramer's rule works, take another look at the solution described at the beginning of 3.1. Okay? Maybe this is where you were talking about. Though I don't think we use Kramer's rule doing it.
No, sir. We
Yeah. It was that's where we used determinants the first time, but we also used the determinant of a 2 by 2 to see if it had an inverse, okay? If the determinant was not 0, it had an inverse. Well, that same determinant we used there is part of Kramer's rule. So we're going to go back to a simple 2 by 2. And we're going to mess with it. And you'll think this is not easy. But it turns out being much easier than you think. Here's your system of equations without having any numbers in them at all except as subscripts. A11 x sub 1 plus A12 x sub 2 equal B1. A21 x sub 1 plus A22 x sub 2 equal B2. Now, with all letters there's no way you can solve that per se, but there sort of is. If you were doing on a 2 by 2 system, you could solve that by elimination by addition. Now, what would be your attack mode there? Here's one suggestion. Multiply the top equation by A22. Now it's going to be A12 times A22 x2, and all these others will be multiplied by that as well. But multiply the bottom equation by negative A12, right? And then this will wind up being negative A12, A22, x2. When you add those two together, they go to 0. So that's what we're going to do. And without having numbers, it's a real pain in the neck, but let's do it. Multiply this top equation by A sub 2, multiply the bottom equation by negative A sub 1, 2. Okay? So this becomes A11, A22, x sub 1, plus A12, A22, x sub 2 equal B1, A22. The second equation, when multiplied by negative A12, you get negative A12, A21, x sub 1 minus A12 A22 x sub 2 sorry, is equal to minus B2 A 12. All right, agreed? Okay, add these two together, and these go out. So now what we have is A11 A22 minus A12 A21 x of 1 is equal to B1 A22 minus B2 A12. All right. Sorry. And that gives us a solution for x1. That's B1 A22 minus B2 A12 over A11 A22 minus A12 A21. That's it. There's your x1. Okay. Now, oh man. Believe it or not, that was sort of the easy part, because the harder part is then plugging this into your original two equations and then solving for x2. Ooh. Okay, so this will be A11 times x1, which is this stuff, B1 A22 minus B2 A12 over A11 B22 minus A22 B2, I'm sorry, A12. Yeah. Goodness, my head is just closing up on me. I can't even think. A12 A21. All right. All right. Now, I'm going to erase this line over here. We've already used it, and hopefully we used it correctly. I didn't check to see if my answer has the right subscripts. The way I'm thinking now, I'm saying no. I'd be shocked if it did. Let's just see what x1 was. B1 A22 minus B2 A12 over A11 A22 minus A12 A21. Yes, well, they rearranged the order, but it's perfectly fine because multiplication is commutative. Now, you may find this is a hard way to do it. You may want to go back to the original and now multiply the top equation by A21 and the bottom equation by minus A11. You may find that's easier. Let's just see. I was trying to see if there is any easy way to do this. And frankly, I don't see it, but plus, oops, get my pen back, plus A12 x2 equal B1. And down here we'll say A21 yeah, I can't get my pen to go where I want it to go. A21, there's where I want it to go. And here we'll plug in the same thing, B1, A22 minus B2, A12. Now the pen's doing whatever it wants to. Goodness gracious. I feel like my whole head is swelling up. Hard to breathe. Over A11, B22 minus A12, B, A21. Okay. Plus A22, X2 is equal to B2. Now, do we need both of those? Not really. Why did I even write the second one? Okay. The first one would do. Sorry. We could solve for that just there. Let me go on and erase this. Sorry about that. Like I said, the brain's not working well today. Okay. I think it may have been easier just go on and restart over again, but we've gone this far. What we want to do is solve for x2. X2. So first thing we're going to do is to subtract this thing from both sides. So let me kind of do it like this. Minus, I'll just wipe it off this side, do a minus A11. Let me write it down here. This is equal to, let me start over. A12X2 is equal to B1 minus A11 times B1 A22 minus B2 A12 over A11 B1 B22. That's an A. Goodness gracious. Keep wanting to write that one as a B, and these are A's. A22, this is an A22 minus A12, A21. Okay. So now we're going to divide everything by A12. Okay. So that gets rid of this. So here's your x sub 2. Now, things are kind of a mess. You say kind of. Probably the best thing to do is just write it down like they did. Sorry about this. You can carry this on through, but it really gets long, boring, and easy to make mistakes. I think probably the better thing was to have gone back to there first. So I'm going to not do it all, but I probably should have left my X2 down there. It's going to do basically what we did above. I thought some things would pan out much faster than they did, so sorry about heading you down that rabbit hole. Sorry. I also want to change this. This time we're going to solve for x2, which means eliminate your x1. So you're going to multiply the top one by a21, and the bottom was minus a11. Okay? And when you do that, these two are going to go away. And you'll have A12, A21, X2. Oh my goodness gracious. No. Sorry about that. Wait. Yeah. I'm acting like I've already multiplied these and taken these out. So now we've got A12, A21, X2 plus, so let's make that a minus, A11, A22. A11, A22, X2, okay, and this is equal to B1, A21 minus B2, A11. All right, just like we did before. So separate out the X2, and what you have is the B1, A21 minus B2, A11 over A12, A21 minus A11, A22. All right. Now I've got them kind of backwards because of the way I wrote them. So let's see what we can determine here. One, I really want to reverse my signs. So I'm going to flip these two and those two. That'll be the same as multiply numerator up and denominator by minus 1. So the reason I want to do that is so these two denominators wind up being exactly the same. So I'm going to write that over here. X2 is equal to, changing the order there, this is a B2 A11 minus B1 A21 over, and your denominators, reversing those, is A11 A22 minus A12 A21. Okay. Now, let's pause for a moment and see what play all this makes. Notice here, your X1 and your X2 have the same denominators, identically the same denominators. Now, not only do they have the same denominators, but those denominators are the determinant of your coefficient matrix. A11, A22 minus A12, A21. You see? Both of those are the determinant of that. So, what we have, I'm going to erase this. So X1, and X2 is going to be the same way too, is going to be, the denominator here is the determinant of A11, A12, A21, A22. The determinant of that coefficient matrix. and that's also going to be for x2. It's going to be something in the numerator over the determinant of a11, a12, a21, a22. Your coefficient matrix. Okay? Now, what about those numerators? Okay? Now, what I want you to focus on right now is the second terms. Okay? The second factors. A22, A12. Okay? A22, A12. And those are the same as these. Okay? Which are A12 is from here, and A22 is from here. Okay? So these are the same there. Okay? Difference here is here you have a B1 and B2 rather than A11 and A22. Right? A11 and A21. So instead of these, we have B's in their place. B1 up here and B2 here. And then, look at that. That's going to be the determinant of that. Now, so let's write that down. This is the determinant of B1, A12, B2, A22. And this one for X2, let's take a look at that. Okay, remember, oh no, okay, I've got it right. Okay, what you've got there, this is A11 and A21 here, and then instead of these two, you've got the B's. B1, so what that, ooh. What your numerator is here is your A11 and A21, B1, B2. Okay, now let's see if that's right. Let's check it and make sure. A11 times B2 minus A21 times B1. Sure enough, that's it. Okay, so what you have, your solutions, this is Kramer's rule. Your solution for any, oh, this is a 2 by 2. For any 2 by 2 is the quotient of two determinants that you can get from those original coefficients and constants. That you don't, there's nothing else there. You're just using those four numbers. It's kind of like the quadratic formula. You just use the coefficients and come up with an answer. Here you're using the coefficients as a ratio of two determinants, one for x1 and one for x2. Same denominators, and the numerators, since you're doing x1 here, instead of your x1 coefficients here, you put your constants, b1, b2, but use your x2 coefficients. And for your x2 here, that same denominator, your coefficient matrix here, take that determinant, and then your numerator is going to be your first coefficients are the same, the x1 coefficients are 5, but rather than the x2 coefficients, we plug in b1 and b2 again. And sure enough, you get the same result. Okay? Now, they come up with a a thing. They call this the determinant of A1. They call this the determinant of A2. Well, what is A1? It's you use the coefficients of your x1, but instead of, no, you use the coefficients of your x2, but instead of the coefficients of x1, which are, that's the variable you're looking for, you put your constants in there. And x2 is, A2 is the same type deal. Leave the coefficients of x1 alone, but instead of the coefficients of x2, which is what you're solving for, you put that. So that then gives you x1 is equal to A1 over A, where A is, this is the determinant of A1 over determinant of A, and x2 is the determinant of A2 over the determinant of A. The determinant of your coefficient matrix, that's the constant, that's your denominator in both cases. The one for your numerator, however, will be you substitute the coefficients of the variable you're looking for with your constants. And here you're looking for x2, so you substitute the coefficients of that variable with the constants. And there you have it. And for a 2 by 2, it can be really easy to do. You know, Zora, you know. All right. That took way too long to describe. Let's do example 3 if we can. And that, by the way, that solution, determinant form of the solution, is called Cramer's rule. So let's erase all this and let's do example 3. Okay. We got a 4x1 minus 2x2 is equal to 10. And you got a 3x1 minus 5x2 is equal to 11. Okay? So what would you do to solve this system of equations? Can you write down at least the determinants that are going to give you x1?
It's going to be 4 minus 2.
Okay. Where are you doing? Let's write down the determinant.
Oh, sorry.
Determinant in the numerator for x1. 10, 11. That goes in place with your coefficients here, and you leave the others alone, minus 2 and minus 5. I did write the problem right, yeah. In your denominator, what do you put? Okay. And your x2? 4. Second? 410. Over the same denominator. I'm not going to write it again. Okay? I'm just going to do that one once and not write it again. Okay? So let's do these determinants. Let's do that denominator first. Now here is a very good reason to do the denominator first anyway. What if that's 0? That means this is not a unique system because this is not an invertible matrix. So you would not be able to come up with an identity matrix any way you did it, okay? So therefore, this one doesn't have an inverse. If it doesn't have an inverse, it's not a unique system, okay? So let's just do that one first. I can do it here. I should have done it here before doing anything else. Just do this. What's that? Negative 20. Second? Plus 6. That's going to be negative 14. So that's your denominator on both of these. x1, I'm going to put the minus out front and put 14 in the denominator. And x2 is going to be a minus out front and a 14 in the denominator. Now, if one of the other determinants turned out to be minus, I'm just going to change that to plus. Okay? So let's do this one. Okay? Here I would write them out. Okay? So what's that? Negative 50 plus 22. So that's going to be a negative 28, right? So that's going to make that a plus 28. Let's do the other one. And what does that give you? 44 minus 30 would be 14. So guess what? X2 is equal to 2, and X1 is equal to 2, X2 is equal to negative 1. Okay? Let's check it and see. 4 times 2 is 8. Minus 2 times minus 1 is plus 2. 8 plus 2 is 10. All right there. Let's do the next one. 3 times 2 is 6. And minus 5 times a minus 1 is plus 5. 6 plus 5 is 11. Yep, that's right. Now, like I said, frankly, lazy as I am, I'm not ever going to write that denominator. I'm just going to write, I'm going to right here to figure out what that determinant is. It's all set up for me. I'll write these down to get that in this place and this one here, and to get that in that place and this one there. So I make sure I get them in the right order and stuff. So I'll go and just do this and put a 14 in my denominator in both places and go with it. That's pretty quick and pretty easy. Now, that wasn't hard to solve anyway. Well, sort of not. Nothing pans out there, so you'd have to multiply. Oh, I think I would multiply the top equation by 3 and the bottom equation by minus 4. And then go, but I think this is going to be quicker than that. Much quicker. Because they're so easy. But of course, that's a 2 by 2, isn't it? It says, Kramer's rule generalizes, I like this, easily to systems of n by n variables. Yeah, I bet you that is going to be really easy to do, right? Okay, the value of each variable is given by the quotient of 2 determinants, just like before. So, again, we're going to do it with letters, which is always a lot of fun, but let's do it. A11x1 plus A12x2 plus A13x3 is equal to B1. Yep. A21x1 plus A22x2 plus A23x3 is equal to B2. A31x1 plus A32x2 plus A33x3 is equal to B sub 3. X's are your variables, the A's are numbers, and the B's are numbers. Okay? We can write down the solution. X1 is equal to, that's the determinant of your coefficient matrix. A11, A12, A13, A21, A22, A23, A31, A32, and A33. And if I was doing that determinant, I'd just write the first 2 columns over again and do it. Okay? And not do it again. Okay? Do it once and have it done. What would your numerator for x1 be? I hope I left enough room here. What would it be? What would be the numerator of x1? The first column is going to be B1, B2, and B3. Okay? And the next two rows are going to be just like what you got underneath. A12, A13, I can't write, A22 and A23, and A32 and A33. That's going to be your the determinant of your numerator, and just repeat the first two columns again and do that. Now you've done the denominator already, so your x sub 2 is going to be that denominator. Not going to write it again, not going to calculate it again. Just calculate it the first time, write it down from there on. How about your numerator? What will it be? For x2. Okay, the first column is going to be A11, A21, and A31. Second column is going to be B1, B2, B3. Third column is going to be A13, A23, A33. Okay? X sub 3. Can you write down its answer? Figuratively. A11, A12, they stay the same. A21, A22 stay the same, and A31 and A32 stay the same. But what goes in the third column? B1, B2, B3. And both of just expand them by repeating the first two columns, and that denominator is going to be that same denominator. That goes here and it goes there. Okay? Calculate that once, you got it done. You have to calculate the other three. So basically, calculate four determinants. The denominator once and each numerator once, and then do the fractions. And they're done. That's done. Is row reduction any quicker? Maybe a little bit, okay? But there are plenty of opportunities for error there. Maybe there are here too, but these are pretty straightforward calculations. So let's do we have time to do example 4? I think so.
Yes.
Okay. You need this up here a little longer? Okay. Nobody? Okay. If I could breathe. Okay. Negative x plus 2y minus 3z equal 1. 2x plus z is equal to 0. 3x minus 4y plus 4z is equal to 2. Do you have any preference of what to do first? Yeah, let's do the coefficient matrix and do its determinant. So what is that coefficient matrix? Negative 1, 2, negative 3, 2, right? Okay. Now, you can do the expanded, or you got one of two options here. Okay? First thing I notice, multiply this by 2, add to that, and you get an equivalent matrix. And remember, that row operation, multiple of one added to another, does not change the determinant. The others, swapping rows, columns, that are dividing and multiplying, those do. This one doesn't. Okay. Or negative 2 times this column plus that column. That would give you a 0 there. So this one gives you a 0 here, that gives you a 0 there. those are the two easy things to do. You want to do either one, or you want to just expand 2 columns and do your diagonals?
The easy way.
Which you think?
So I feel like I just doing the row operations real quick.
The what?
I feel like the row operations really quick.
Yeah. Yeah, and you want to do the row operation here, or the column operation there? Huh? Doesn't matter. It really doesn't, because they're almost equivalent. So let me do, because the numbers are smaller, let me do minus 2 column 3 plus column 1. Is that okay? All right. So this will then be equivalent to, we're going to keep the second column alone, 2, 0, negative 4, and keep the third column alone, negative 3, 1, 4. And then the first column is going to be minus 2 times this. That would be a 6 minus 1 is a 5. And a negative 2 plus 2 is a 0, exactly like I wanted it to be. And the next is going to be minus 8 plus 3 is a minus 5. Okay? Now, that's a pretty easy determinant to do. What's your first step? Yeah, you want to use that 1, don't you? Yeah, you want to use that row, don't you? And if you're using that 1, you're going to wipe out that column, don't you? Okay, so first thing you determine about that 1. What? The sign of that position. And what's the sign of that position? What'd you say? Yeah, negative. Plus, minus, plus, minus. Plus, minus, plus, minus. Any way you get there, it's a minus. So that's going to be a minus 1 times, and then just do this. What's that? Negative 20 plus 10. And that's going to be minus 1 times minus 10 is 10. There's your denominator, right there. So your x is going to be something over 10. Your y is going to be something over 10. And your z is going to be something over 10. We got to figure out the somethings now, okay? So, what would be your x something? 1, 0, 2. 2, 0, negative 4. Negative 3, 1, 4. That determinant. And look at that one. Don't you love it? You got a row set up for you already. And that's going to be, so again, that position is the position, sign of the position. Negative again, so it's going to be a negative 1 times, and then just do your, let's say, second, negative 4 minus 4, so that's going to be a negative 8. So this comes up being 8. So x is going to be 8 over 10, which is 4 over 5. Done. There's your x, right there. Okay, what's your y? What determinant is that going to be? Wait a minute. Don't tell me I've done this. Wait a minute. Y'all let me get away with this? No. It's fine. It's fine. Oh, man. What's its determinant going to be? What's that matrix going to look like? Negative 1, 2, 3. That's that first column. What's the second column? The y, that's where you put it. For the y, you put in your b's, the constants. Remember? You put in the b's here for the x, the here's for the y, and here's for the z. You put in this column instead of the coefficient. The denominator was the whole coefficient.
Oh, I got twisted.
Yeah. I'm doing this probably weirdly. So what's your middle column there? Oh, you do too. It's that 102.
Oh. Okay.
See, that's what goes in instead of the coefficients for y. And what's your third column?
-3, 1, 4.
Perfect. All right. Now again, you got a couple choices here. They're exactly equivalent. I mean, you got three choices actually. I think I'd just as soon do a row operation now because I'm a little more used to those than column operation. So let's do -2 row 1 plus row 3. That's sort of easier than going backwards, right? So this is going to be, we're using row 1, so that stays the same, -1, 1, -3. Okay? We're leaving 2 alone, so that's 2, 0, 1. But we are changing row 3. What would it be? Okay, it's -2 times -1 is? No, it's going to be +2. -2 times -1.
Oh, time. Okay.
Yeah. Right? And add that to 3, and you get 5. Next, -2 times 1 is? -2 plus 2 is 0. That's what we wanted it to be. It better be. Okay. Next one's going to be -2 times -3 is +6. Plus 4 is 10. Okay. There's your determinant there. Okay. Now, wait a minute. Yeah, okay. All right. We want to use that column, right, because that's got the zeros in it, and of course that row. So, what is the sign of that first position? That's a negative, okay? So it's going to be a -1. I'm going to do it over here. -1 times, and then let's crisscross. 20. 5. 20 minus 5 is? Yeah, it's going to be a 15. 20 minus 5 is 15, but we have a -1 in front of it, so that's going to be a -15. So your y is going to be a -15 over 10, which is -3 over 2. That's a pretty ugly 3, okay? Got that one? All right. What's your numerator of z going to be? Let me, I almost want to leave that, but I'm afraid it'll be confusing if I do. So let's make a determinant here. I'm going to have to write small. Oh, we can go and erase this. We already have it. That's your determinant of your denominator is 10. Determinant of your denominator is 10. Okay. What's your matrix for your z? Your numerator matrix for z? Okay, don't change the sign of it. It's -1. Which way are you going, up or down? Or across or down? Down, okay. 2, 3, okay, got that one. How about the next one? You do this one. You keep that, yeah. It's only the third column. The Z coefficients are the one you change. Leave this one alone. 2, 0, -4. And then here you put in your B, which is 1, 0, 2. I love it because you already got a row of zero, not a row of zeros, but a row with 2 zeros in it. So how do we calculate the Z? The numerator for Z. We already got the denominator. Wipe out that row and that column. And then choose your sign here. What's your sign there? No. Plus minus. The position sign. I should have said that. So that's going to be -2 times the determinant of what's left. And what's that?
4. So it's -2 times 2.
Okay. 4 plus 4, because it's an up one, so it's the minus of it. -4 times 1 is -4, but it's going up, so you negate that and make it 4. 4 plus 4 is 8. So that numerator is going to be -16. So your Z is going to be -16 over 10, which is -8/5. Right? Let's see how they did. They got their X to be 4/5. Good for them. Oh, that's all they did. They said use Kramer's rule to solve the system of linear equations for X. They didn't do the Y and Z.
The Y and Z is on the remark.
It's on what?
It's on that remark on the bottom left home page.
Oh, here it is. I see it. Okay, the remark on the left-hand side. -3/2 and -8/5. Good deal. There it is. Okay. We did what they remarked for us to do. We went on and solved for it. All right. I think we're within just a couple of minutes of being out of time, aren't we?
2 minutes.
2 minutes. Okay. So I think we'll start next time with, at the top of page 132, area, volume, and equations of lines and planes. Wow, that sounds like a lot. But you'll see these go pretty quickly, and they build on each other. So we'll start with that next time. Oh, then we got some more things to do. So anyway, exercise 3.4 on page 136, 137. Okay. I would say do any of the odds 1 through 7. They should all be at Calc Chat. Do number 9. It's a proof if you want to. I know that Keystone wants to do that, but anyway, that's number 9. Knock yourself out. Do number 11. That should be at Calc Chat. Do 13. It should be at Calc Chat. Another proof, 15, at Calc Chat. Should be. Then do any of the odds 17 to 29. They should all be at Calc Chat, and that's using Kramer's rule. And then either 31 or 33. Okay, they should be at Calc Chat. 35 should be at Calc Chat. And stop there. We'll pick up the rest of those next time. Okay? So, not only do you have an extra weekend to work on your test, unless you turn it in early, you also have the rest of this week to work on the test. Because I think we'll finish it next time, but the test isn't due until 1 week from the time we finish 3. So you're still okay with it? Okay. Good deal. And we'll pick up and go from there. Now, how much did I cheat you out of your tuition dollars